Hello, this is the course of data engineering, and I would like to continue from the previous videos, and it is about the imputation methods. If we already learned about the previous videos, we learned about the concepts and we learned some basic approaches for handling the missing values. These methods, we call it the imputation methods. What does it mean by imputation? Impute, we want to replace, we want to change, or we want to fill in the missing values. That's the meaning by impute. Or we can we can replace, or we can fill in. So there's another word for this imputation. There are some methods for the imputation. First, we can do the random sample. So we can have the random sample from the existing values. It means you can randomly generate an integer from 1 until the n minus n missing, and then replace the missing value with the corresponding observation that you choose randomly. So yeah, any value random. Let's say you have the y1 and then you have y2. Okay, this is the data, no problem, no missing values. Oh, sorry, maybe I need to. Okay, so let's say this have no missing value, and this one also have no missing value. Okay, but oh, this one have one. Okay, and how can you replace this one? So I can random generate number between 1 until 9. So this is number 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I can generate any number. Let's say I want to get 3. Okay, then you will get, what is the value 3? Okay, 4.9. Then yeah, you will replace this NA with 4.9. Okay, this is the random sample, and of course the advantage, it may change the distribution of the data. Yeah, no no other methods that could. Yeah, I mean, of course each method have their weaknesses, but this is the best way to replace the missing value if you want to still do the analysis. The other kind of method is randomly sample from a reasonable distribution. Let's say if gender is missing, and you have the information that there are about the sample number of females and males in the population. Okay, so let's say you have the gender. Okay, and then you have like 10 data, and then some data are missing the male and female. We know that the population in Yongin, let's say this is the data about the people in Yongin city. So I have like 10 data, the person in Yongin city, and I have the population in Yongin city, maybe 60% is male and 40% are female, for example. Then yeah, some missing values you can fill in to fit with this distribution on the population. Yeah. Yeah, in this example, yeah, I put like the Bernoulli, the Bernoulli distribution. Yeah, the Bernoulli distribution, or estimate P for the observed sample. In using random generator from the Bernoulli distribution for P 0.5 and generate number for missing the gender data. And the disadvantage is the distributional assumption may not be reliable. Yeah, there's a weakness. Okay, but even the assumption is correct, its representative is still doubtful. Yeah, of course you need to, yeah, this is one of the way. Okay, but the disadvantage just kind of notice for us. If you want to do the imputation, of course there's a risk for this kind of like the representativeness. Okay. So the other imputation method is about the mean or mode substitution. This is the most common imputation methods. We can replace the missing value with the sample mean or mode. Okay, we know the mean. Mean is the average, okay, of the numerical value, and mode usually we use this for the nominal variable. Okay, usually this is for the nominal, and the mean is for the numerical. Or sometimes we don't use the mean, but sometimes we can use the median for replacing the missing value. And when you already have the value, then you can run the analysis. Yeah. The advantages, we can use complete case analysis, but the disadvantage, we can it reduces the variability, and it weakens the correlation estimates because it ignores the relationship between variables, and it creates like artificial band. Unless the proportion of missing data is low, then do not use this method. Okay, so if the proportion of missing data is okay, that's quite low, then okay, you can use this one. But if you have a lot of missing data, maybe you need to consider another strategy. Dummy variable adjustment. So we can create an indicator. You can create an indicator for missing value, like say 1 for missing and 0 for observed, and impute the missing value to a constant, a sample mean, and include the missing indicator in the regression. We say this is the dummy variable. For example, if you have the if you can use the missing value as a constant, it means like the numerical variable. If you don't have the missing value, and then you can have like the one-hot encoding. Okay. So I have not explained to you, but I hope that you can understand. In the one-hot encoding, we can have like the 0 and 1. Let's say I have the country. Okay, so I have the country name, the country of a person. So let's say the country of a person is he is in Korea, he is in USA, and he is in Indonesia, for example. And then when I do the one-hot encoding, oops, yeah, I can replace this data into like Korea, Indonesia, USA as an attribute. And if it is a Korea, then it is 1, and the Indonesia is 0, and USA is 0. And the second is USA, so Korea is 0, and then the Indonesia is 0, and USA is 1. And if it is Indonesia, okay, and we have the 0, 1, and 0. So what about if it is missing? Okay, so we can make the dummy variable. So we can have like this dummy is missing. Okay, so we just put 1, 0, 0, 0, and 1, and we can have still 0 like this one. So with this kind of adjustment, yeah, we can use all the information we thought about the missing observation, but the disadvantage, the result is in bias estimates, of course. Okay, there's a bias, and it generates a new attribute. Of course, it will be the dimensionality, curse of dimensionality. Okay, you have the curse of dimensionality. In this case, you will create another dimension, and yeah, it will be more time consuming. Yeah. And it is not theoretically driven. Yeah, it's just a very simple strategy or a practical strategy. Another way for imputation, we call it as a regression. Okay. When we do the regression, means we can replace the missing values with the predicted score from regression equation. So we can make a regression, and then we use the complete cases to regress the variable with incomplete data on the other complete variables. So yeah, this the easy way for doing the imputation. And the advantage is how we can use the information from the observed data, and it gives better result than the previous one. The disadvantages is the overestimate model fit, because we already know the regression. Okay, so when we have this regression and you want to fit the number with this, okay, of course it will overfit, overestimate the model fit, and yeah, it will overestimate the correlation estimates, and it will weaken the variance. Okay, so this is the strategy for the regression. Let's say, yeah, regression, we can have this kind of regression. Maybe this is from the idea from this data. Okay, so we have this data, we have this observation, okay, and we can put this observation into a regression model. Okay, so we can try to make the regression, and based on the regression value, we can try to predict what is the best value for this NA. Okay, so what we can do is, let's say we have this parameter, okay, y2i equals to the beta 0 plus beta 1 multiplied by y1 comma I. So we can just use the data from 1 until 9, and we can get the beta 0 parameters like this one, and the beta 1 parameter as this one. And then, yeah, we can get the expected value. To get the expected value is the, we can make like the model, okay. The predicted value y2 equals to this coefficient minus 0.366 of the variable y. Then, yeah, I can figure out, okay, I can figure out this data. Let's say if I know the y1 is 3.6, okay, how we can get the 3.6? Yeah, if I know there is a correlation between the y1 and y2, so I know that the data here is 3.6. Then what is this data? Okay. So because I know the data is 3.6 for y1, so I can just input 3.6. Sorry, I can just input the 3.6 here, and then I can get the value. So this is the estimate. Yeah, so 5.24. The regression assumes responses are normal distributed. What is the assumption is unrealistic. Yeah, you can still use another models like logistic regression, and yeah, of course there are many other regression models that you can use for this. My maximum likelihood estimation. So this idea is to identify the set of parameter values that produce the highest likelihood here. Because this is the ML estimate, or the maximum likelihood estimate, is the value that is most likely to have the resulted in the observed data. Oh yeah, we can use the regression, or there's the log likelihood. The highest log likelihood, usually we use the probability. The advantages is useful information, both complete and incomplete, to calculate the log likelihood, and it is unbiased parameter estimate with the MCAR MAR. However, the disadvantage is the standard errors bias downward, but this can be adjusted by using the observed information matrix. So if you already have the observed information matrix, then the standard errors can be more adjusted. So let's say I can have this maximum likelihood with the expectation maximization algorithms. Okay. So we have the distribution. Okay. This is the case 1, and then this is the case number 2. So start, we will guess the probability distribution of parameter Okay, so we can have the variance and the mu. Okay, and after we have those data, then fit new data into the initial distribution. And what is the probability xi came from the yellow, and what is the probability that the xi came from blue? Okay. And then after you know that the probability it goes to blue is some value and it goes to the yellow is some values. Okay, then we need to calculate the new variance, and we will calculate the new mu. Okay, so after we calculate the mu and the variance, so we will check whether it is stabilized or not. Okay. If it is stable, okay, if there is no changing with this mu and the variance, then yeah, let's finish. If there is a changing of these values, if it is not stabilized, then okay, we need to update. Okay, so we need to update again with the new parameters. Okay, after we have new parameters, so yeah, you can have the initial value again, and then check again. Yeah. If we are guessing with the new missing value or with the existing missing value, so we can put another data, and then what happened with the distribution. So until it is stable, then yeah, we can finish this kind of imputation methods. Of course, if your data missing is only one, yeah, it's simple. But if your data means the missing values are a lot, yeah, this kind of repetition will consume a lot of time. And of course, we have this algorithm, okay, for doing the optimization. This is based on the clustering approach. Okay, so I can do like the summary. Okay, what is the simple approach to handle the missing values? Okay. Yeah, if some single imputation methods under non-MC are missing this example, we can let's say we have 4 cases are missing, then yeah, we can just try to adopt this the same value or the global variables to replace the missing values. If we are doing with the min substitution, yeah, we can replace the missing value with min. If we use the hot tag or random borrowing, okay, so if we know the class of that particular data, then yeah, we can just put this into this missing value. If we have the regression, then it means yeah, the value will be the same with the line in the regression. And if we have the regression and conditional noise, yeah, then you have noise, and of course you can put it the easy conditional noise, or you can also use this one with uh, the maximum likelihood. Okay, the ML maximum likelihood, yeah, because it also consider the distribution of the data itself. Multiple imputation. This, yeah, when we have the imputation, we learn about the random. Okay, we learn about how to use the mean, and we learn how to use the regression. We use the maximum likelihood and etc. We can combine the imputation methods. So the idea is to replace each missing item with 2 or more acceptable values. And yeah, we can represent a distribution of possibilities. Okay, then we can use like to replace with the mean, and then we can replace with the maximum likelihood, and then we can find the distribution of possibilities. And then this result in M complete data set, each one is analyzed using standard methods, and estimates parameters are average. Can often be generated from single modification of existing single imputation method, such as hot tag or regression. Okay. So there are some things that I think this is the idea. Okay. when we have the missing value, okay, so this is the missing and this is the missing and this is the missing, we want to have the m imputation. So this is the method, maybe this is the method 1, method 1, and then this is method 2, method 3, and method 4. Okay, so until method, yeah, m. Let's see. So we want to have some alternative when we want to replace it or when we want to impute it. The most useful when the fraction of the missing value is not excessive and when m is the modus. Okay, so maybe between 2 until 10. So the multiple imputation, it can be something like this one. You have the incomplete data, and then yeah, there will be some multiple imputed data. Maybe this is the mean, this is the maximum likelihood, and this is the regression. Okay. And the process starts with the incomplete data on the left side, which is imputed m times. Yeah, that's created m complete data set. Its complete data set is analyzed using standard complete data software, and thus resulting in m analysis result. So we can analyze, and after we analyze, these m results are put into one final result that adequately reflects the amount of uncertainty in the estimates. So the final result will give you the uncertainty estimation. Okay. There is one rules, we call it the Rubin rules. So this is the formula. Okay. When we impute a value, so we will get a new average like this one, and then we will try to figure out the variance. Okay. So this variance of Q1 divided by M, we will get the value of W. Okay. And after we have the W, we want to calculate the P. What is P? P is, we want to see the difference between the possible value of Q. So it is the every values that you have in the data set, you subtract by the original value. Okay, sorry, this is the mean. Okay, the mean here, and then after you have the P, okay, so you have the T. T is to indicate how the variance, and then the P itself, this one is the P or the difference, and we want to multiply with the P divided by M. M is the number of the multiple imputation methods here. So if we have the T, then we can try to make the estimation whether this uncertainty in the estimates is good or not. So the how to fill in the values, yeah, we have the Bayesian perspective. Okay. So in the Bayesian perspective, it means we draw multiple imputations to simulate a Bayesian posterior distribution of missing values. That is a conditional distribution of the missing data given the observed data. So this is the, I think if you already understand the Bayesian, yeah, we have the data and then we have this observation and R in. What is it? So R in is the set of units included in a sample. Okay. So this is the missing values when you include it in the samples. Okay. So there are some options, and then I is an indicator for the inclusion. Okay. So if it is, yeah, you have like some weights, for example, that can be the indicator for the inclusion. So the way is to impose a probability model on the complete data and non-response mechanism. So for example, if it is a normal regression or log linear model, yeah, so we can have the probability and we can have the non-response mechanism. Okay, so the non-response mechanism means not the target. Okay. the target or the class, you call this is the response. So if we have the other x and y, so yeah, this is the non-response. Okay, the non-response. And yeah, we can create the imputations through a two-step Bayesian process. The first is we can specify the prior distribution and draw the unknown model parameters and simulate M independent draws from the conditional distribution of the missing data given the observed data. So like what I explained to you, the probability. So we need to specify the prior distribution. This is one of the important part in the Bayesian. Okay? When you have the distribution, you need to specify it. If you don't specify it, then yeah, you can base on the data, okay, but you based on the observation. Yeah. This one you can use the observation to set the prior distribution. Okay, and yeah, you can draw the unknown model parameters based on the prior distribution. This requires deriving the posterior distribution. Okay. In simple problems, it is a closed form solution axis. So closed form means there will be a kind of ranges usually. Okay? So there will be no such open form. In open form solution, there are many solutions, but in the closed form, yeah, we have some ranges of values. In a more complex application, it rely on spatial computational techniques. Yeah, if we want to have more simulation approaches like the Markov chain, yeah, Markov chain Monte Carlo MC, then we will simulate if this data is replaced with 5, what is the probability distribution? If the value is replaced with 6, what is the probability distribution? If this value is replaced with 6.5, what is the probability distribution, and so on. Okay, so we can use the Monte Carlo, the Markov chain Monte Carlo to understand this kind of posterior distribution. There are some other possibility. Okay? So there are some papers. Rubin in 1987, he proposed approximate Bayesian bootstrap. So after we have the Bayesian, and then we will accumulate, and then we have another Bayesian, and then we accumulate, and we have the another Bayesian to, yeah, it's kind of bootstrap. Okay? And modeling propensity score to form sampling groups. So there's another method to find the posterior distribution. So the approximate Bayesian bootstrap, maybe I will just explain briefly. I do not want to discuss the detail because, yeah, if you want to see the details, yeah, you can see the paper. Okay, so he discussed about the Bayesian bootstrap and how the Bayesian bootstrap can be applied to the approximate Bayesian bootstrap. So the idea is only how we can draw n1 value randomly with replacement from the observation. So it means the hot tag. Okay, so I already explained to you about the hot tag. And then draw the n0, which is n minus n1 components of y, which is missing, randomly with replacement from the y star observation. So y star observation means the value that you already observe with the replacement. Okay, then we can accumulate again. Yeah, this is the observation that you miss, and then you replace it. Okay. So the paper in the Rubin, it mentioned that when you are doing with this kind of multiple imputation, there should be limit with the M. Okay. M, what is M? M is the number of methods for the multiple imputation. Okay. So if you have the very big M, yeah, if M is big, of course, it will cost a lot. If M is too small, maybe, yeah, the distribution will not be representative. So in Rubin, he has a formula to show the relative efficiency of the finite M estimator. Okay. So this is the equation to indicate the finite M estimator, and Y, gamma is the rate of missing information for the quantity being estimated. Okay, so for example, for small gamma, okay, for small gamma like this one, M2 or 3 is nearly fully efficient. Okay. So here is like this is the percentage. Okay, so the efficiency is about the percentage. When M equals to 2 or 3, okay, small gamma is nearly fully efficient. So its efficiency, yeah, it means you don't need to have so many M. Okay. When you have the M is like unlimited, yeah, so it means you have many methods. So if you have many methods, what happens? Oh, whenever the gamma it changes, it will give you nearly fully efficient. But of course, yeah, it will make you it's time consuming, what I said. Okay? But if you have very small m, maybe the gamma should be also small in order to fit with the efficiency. Okay? Because if the gamma is higher, you have the efficiency score is less or is lower. Yeah, we already deal with many methods, okay? And you can have your own ways to handle the missing values if there is any missing value in your data. Okay? So the advantages of this multiple imputation or the imputation method, it allows to use standard complete data methods. And you can incorporate data collectors' knowledge to reflect the uncertainty about the imputed values. So when you use the multiple imputation methods, of course, you need to reflect the uncertainty. And if you can reflect the uncertainty, of course, it will create a good data. Yeah, this means that the sampling variability and uncertainty about the reasons for non-response. And it increased the efficiency of the estimation. So when we are doing with this multiple imputation methods, yeah, it can increase the efficiency. And it provides valid inference, of course, when you have multiple and you want to tell which one is the best one, yeah, it will provide the valid inference for this one. For example, the variance estimators, it will be more valid. And especially if it is under assumed model for the non-response. And it allows one to study sensitivity to various models. So if we have the m equals to 1, yeah, whether it is sensitive to regression or not. If it is m equals to 2, yeah, whether it is sensitive for the log regression or linear regression. If m equals to 3, then yeah, you can also think whether the result can be also for the linear regression or log regression and other stuff. For example, if you want to know the sensitivity for the models that you created for your machine learning. Okay. And yeah, the disadvantages, of course, more work is needed to generate multiple imputation. Okay, of course, the result is good when you have the multiple imputation, and this is the as the literature mentioned, this is the best way to impute if you want to get a good model. Yeah. It is often not difficult to implement using the existing simple imputation scheme. Yeah. But yeah, of course, still you need more work to handle this one. And it requires more space, okay, to store the data. Because you need to impute with the strategy 1, you need to impute with the strategy 2, you need to impute with the strategy 3. Of course, you need to have more storage, and it requires more work to analyze the data. Yeah, not serious when M is the modus. It is often not difficult to implement using standard statistical programs. So if you use like the SAS, or if you use the SPSS, it seems it's not that difficult, okay, because they have the function. But when you do with the Python, of course, it requires more work. Yeah, I cannot explain to you about the Python, so I give you this code in the literature, so you can have like this code if you want to understand the Python code. Yeah. So I hope that you can have the idea, the concept for doing the imputation. And in Python itself, they have the project IMP youth. Yeah. So you can check. There are already some basic functions for this imputation. Okay, so yeah, we already learned about the definition of missing values, and there are some approaches for missing values. Okay. We can delete, or we can impute, or we can do the multiple imputation. So the multiple imputation is a method for replacing missing value, which has some theoretical advantages over other methods. And yeah, software is becoming more common to handle multiple imputation. So yeah, I guess it will be good if you have your missing values, yeah, because you are as a graduate student. I guess I can recommend you how to deal with the multiple imputation. Okay, I think that's all for this course, and I really appreciate your participation in this course. Thank you very much for listening, and hopefully we can meet in Zoom for next course. Thank you.